Sorry, this video got broke up. I accidentally hit a button that caused it to stop recording. So here's the second part. So in this one, we're going to have to actually scale our area for this. If I wanted to get all of it, then maybe I would say, what is this, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So we could scale this by tens, being 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Okay? Now keeping in mind, if I'm scaling it this way, then all my points are going to be approximate since, you know, none of them are falling as pretty points anyway. So at 0 folds, I have 93 and a half. Well, that would probably be just right about there. Well, actually a little lower than there. My orientation's a little off. At 1, I've got 46.75. So 46.75, you'll notice, is going to be really, it's going to be way down here. Don't you see that? That's a pretty good little difference in area. After that, the area starts getting smaller and smaller, the difference. Then we go down to 23. So this will be 23.375. 11 right here. I got 5 point, so I don't know if that's an 8, 9, or, but we'll do 5.8, which will be right about there. Then I got 2.9. Well, that'll be right about in here. Then I got 1.46. And what you notice is as I'm doing this, these points are getting closer and closer to 0. And it doesn't matter how far out I go this way, it will never get to 0. So long as I'm folding, I will always have some kind of area, because for me to have no area means that the paper doesn't exist. And since the paper does exist, so what you're talking about, the longer I go, the more I fold, the smaller the area gets, but it will never actually reach 0. It will simply get really, really close to 0. It's like having a lower boundary. It can't cross the x-axis. And it actually is. It's called a horizontal asymptote. And our horizontal asymptote is going to be y equals 0. It will never touch it. It will just approach it. Okay? So looking at this, this is actually the equation. So we've done y equals mx plus b. We've done ax plus by equals c. We've done y equals m, x minus h plus k. All of those for a line. Well, this is going to be your equation for a exponential. A is going to be the start. In other words, kind of like b in y equals mx plus b is the y-intercept. Well, now a is the start. B is going to be the constant rate of change. It's going to be that rate, that ratio of change. Okay? So and you have to be real careful with that, because remember, we're used to B being the y-intercept. A is now the y-intercept. So in our first scenario, the sections versus the number of folds, our y-intercept is 1. And if you go back up here to your table, that's going to be your A value for both. So our area A value is 93.5. And that's the one you'll notice is also sitting on the y-intercept. These are your two y-intercepts. My B value is going to be, what are they changing by? Well, over here we decided that the number of sections, or as we folded it, the number of sections were doubling. So our B value is actually 2. For the area, well, those we said the B value, the constant rate ratio, it was multiplying by a half because they were cutting in half, right? So if I were to write these equations, I would put y equals 1 times 2 to the x. Then this one would be y equals 93.5 times 1/2 to the x. Okay? Notice, just like y equals mx plus b, you have still got your y and your x. They don't go away. You simply replace the a and the b value. So then we could use our calculator to determine how many folds would it take to make at least 10,000 sections. So what I want you to do is plug the equation into your calculator. Let me get my calculator and do it. Okay, start off on the calculator. We're going to hit home 1, no. So we start fresh. And we want to go with a graph, because that's what we're going to do. We're going to enter this into our graph. So I have 1 times 2 To get it to go to the exponent, I hit this button right here, the caret, and to the x, and push enter. We now also, it says how many, we use your graphing calculator to determine how many folds it would take to make at least 10,000 sections. Well, keep in mind, to know that, we've got to know what's x and what's y. Every time we folded, that was our x value, so the 10,000 sections, this is actually a y value. Well, that means in our calculator, we want to put y equals 10,000, because all we have to do is find out where those two intersect. So if I go back over here, I'm going to hit tab, and I'm going to type in 10,000 and push enter. Now, keeping in mind, this only goes up to 6.5, so I need to click on that, and I'll change that to 11,000. And that'll get it to transfer up. Now you can see my red line is that horizontal line of y equals 10,000. I want to see where these two cross, and you can see it's way over here to the right. I'm going to try just doing menu, and I'm going to try to do the window, and I want to do zoom fit. And if you'll notice, I can see my whole blue, but once again, I still can't get to that 11,000. So I'm going to have to do this, I'm going to have to do a little more work manually. So let's see. I'm going to do menu, and let's try window. This time, let's just do zoom out. So anytime you're doing this, you can just sit here and zoom out until you see, oh, that's horrible, until you see what you want it to do. So there we go. That's exactly what I want. I want to see where the two intersect. Now I want to find out, given that, what's that value? So I do menu, analyze graph, and we're going to say intersection, because that's what we're interested in. Where do they intersect? We want our lower bound to be clicked on the right side, and then we're going to do the left side. Sorry, I lost mine for a second. Analyze graph, intersection, we'll do it on the right side and the left side. And then it'll give you your intersection. It tells you at 13.3, so at 13.3 folds, it will intersect with 10,000. Now here's the problem. I can't do a third of a fold. I either fold it or I don't. So while x may equal 13.3, to actually answer this question and have at least 10,000 sections, I need 14 folds. And that will get me to where I have enough sections. Okay? So now using the other one, I'm just going to start it over, and let's clear it off. Let's look at entering, once again we're going to go to a graph, and we want to enter 93.5 times. This time we're going to do 1/2 to the x. Okay? Push enter. There's your graph. It's over here. This time I want to know how many times you're going to have to fold it until you get an area that's less than 1/100. Once again, that area is a y value. So I'm going to simply type in y over 1/100. So I come over to my calculator, hit tab, and I have 1 divided by 100. Push enter. I'm interested in where these two cross. It's going to be somewhere out to the right. So let's see, I'm going to change my window, and I'm just going to go, my max x value, I'm going to change it to 20. Okay? And I think they might have crossed by now, keeping in mind that it doesn't matter how far you go out to the right. For example, I'm going to change this to 1,000. I don't know if I got 1,000, but you'll notice that blue line is not down here in the bottom. It will not cross the x-axis. So now I'm just interested in where did my two lines intersect. Let me move these out of the way so we can actually see a little bit. So I'm going to hit menu, analyze graph, and I'm looking for the intersection. I'm going to get to the left, and then I'm going to get to the right. And it says that 13.2 is when it is actually 1/100th. So the answer, 13.2, however, that doesn't really answer the question because, once again, I can't have part of a fold. So this is where you have to be careful. Make the area each section less than 1/100. Well, keep in mind, as the more folds we have, the smaller it gets. This is actually at this. I'm going to need to fold it completely. I would have to have more than that to get it smaller, right? So this scenario, I'm going to need 14 folds, because when I get exactly to the 14th fold, my number will be smaller than 1/100th, because you'll remember these are cutting in half. So it would actually be 1/200, okay? Okay, so now let's go ahead, and now that we've kind of introduced the idea of an exponential, I want to go to this page. This is kind of a page that will give you an idea on writing these, and then we can look at the classwork a little bit together. If I look at sometimes it's difficult just to figure out what the rate of growth and decay are. So that's the purpose of this right here. It's giving you all the pieces, and right now my focus is on showing you how do I find out if it's growth or decay. So for example, say you're told the number of bacteria in a certain culture doubles every hour. Well, that was basically what was happening in our last scenario. So if it's doubling every hour, that means it's multiplying by 2 over and over, so my common ratio is going to be 2. Therefore, my B value is 2, because the common ratio is the same. It is that B value. It is that constant rate of growth, okay? So then we have the number of bacteria in a certain culture triples every hour. Well, this now means that my B value is 3. If it's tripling, that means I'm just multiplying it by 3. It's a little different when you're talking about a percentage, though, okay? So what I want you to think about, take a second, and let's just think about an idea. Say I have $100. Whoops, not 1,000, 100. Oh, I should have known 1,000, that's better. If I told you my $100 was doubling every hour in this awesome investment I had made, how much would I have after the first hour if it were doubling? Hopefully you realize, well, it's multiplying by 2, so it would be 200. So what I want you to think about, to get to that 200, I had to include my first 100%. I had to have 100% of that, plus I needed this as well, which would be another 100%, right? 100% plus 100%, well, I got 200% growth. Turn that into a decimal, and I have 2. That's how your percents work out. So let's see if we can see that makes sense. The population of a certain animal species increases. This is how it's always going to work. 1 plus or minus whatever the percentage is. And the percentage needs to be written as a decimal. So that percentage is the rate, okay? So in this case, I have 1. If it's increasing, that means plus, right? That's just common sense. If something's increasing, we're adding. And then it's increasing at this rate. Well, 1.26%, if I'm going to turn that into a decimal, I got to move. So I got 0.0126. So I got 0.0126, which will give me a rate of 1.0126. The 1 represents the original amount, the 100%, plus this right here is what it's growing by. So let's try that again. Here I've got a computer's valued at this amount. My rate is 14.3%, so I got 14.3%, but then if I turn that into a decimal, it's going to be 0.143, okay? But it's depreciating. Well, if it's depreciating, that means it's losing value. So this is take the original value, the original 100%, and subtract the rate that it's depreciating by. So then I have 1 minus 0.143, and I'll end up with a rate of 875, sorry. Oops. So if it's less than 1, that's a good way for you to know that it is actually decaying. Okay, see if I can pick up where I left off. Sorry, I got interrupted. A car depreciates 9% each year. This is the one, whenever you have these depreciations, you'd be surprised how many of y'all, when y'all write it, all of a sudden I got a car and it's increasing in value. When it says depreciate, it's talking about decay. And if it's decay, that means that that value, that B value, will be less than, not zero, that wouldn't be good. It will be less than 1. In other words, it's going to be a fraction. It's only going to be part of the original value if it's decaying. So if my car is depreciating by 9%, that would be 1 minus, and 9% would become 0.09. So then I have what do I got? 91. And this is telling me, well, it's depreciating by 0.9, but I'm actually interested in what is the car still worth. It's worth 91% of its original value, okay? So going with that idea, let's do one of these ideas. We'll do the rabbit together, okay? Do I want to do the rabbit together? It's discounted. Now let's do the car. Let's do the car one, because you've got one that's this is an increasing, so this is going to be growth. This one is a depreciating, so it's going to be decay. Since this is growth, your B value will be greater than 1. Since this is decay, your B value will be less than, oh, I went to put 0 again, will be less than 1. And then down here, you can decide on that one. So looking at this, what's the independent variable? Well, the independent variable is going to be the x, the dependent is going to be the y, but you have to figure out what they are. Well, as what? Every year goes by, my car is going to depreciate by 15%. So as every year goes by, that would be my input. 1 year, 2 years, 3 years. So number of years. Well, my answer then would be the output, which would actually be, well, what's the new value of my car? So now what's the A value? Remember, the A value is the starting value. At the beginning, at 0 time, my car is worth $35,000. And then since it's decay, I'm talking about 1 minus 15%. 15% as a decimal is 0.15. 1 minus 0.15 is 0.85. Oops, I didn't want that there. I wanted that right here. So now we just have to plug these numbers into our equation. So I have y equals A is 35,000. I'm going to run out of space. Times, hold on, let me erase this so I can make a little room right here. Times B, 0.85 to the x, okay? And notice all I did was go back and I used that same equation that we had right here, okay? So now you can complete the classwork. And we're going to move on to our next part of law of exponents. Last time we did when multiplying like bases, we added the exponents. Now we're going to talk about, well, what if I'm dividing, okay? So looking at this first one, I got 2 to the 4th. And once again, let's remember, the B, well, this is the base, and the A, well, that's going to be our exponent, right? So now, looking at our first one, I have 2 to the 4th, which would be 2 times 2 times 2 times 2. And then I've got 2 squared, right? Well, if you were doing this, maybe you remember, well, these will cancel and become 1. These will cancel and become 1, right? Because 2 goes into 2 one time. And I'm left with 2 times 2. I'm left with, in other words, 2 squared, which equals 4. And remember, we're looking for a pattern. Just like when we were multiplying like bases, we add exponents. There's something going on here, too. When I look at this one, I got x times x times x. I got x times x cubed over x squared. Once again, these will cancel these, and I'm left with just x to the first. So what you may be noticing is, oh, look, x, dividing like bases, I subtract the exponents. 3 minus 2 is 1, x to the 1, okay? Now, there's another way I like to show this because it can get a little confusing sometimes. So the way I'm going to tell you to do it is, hold on, do I want to break it out for you? The way I'm going to show you to do it might be a little easier for you. I could write all this out, but I've already shown you where the idea is coming from, so instead I'm going to show you my little cheat. I want to do it like base to like base, so I'm going to focus on my x's first. My question for you is where it's the bigger x. Is x squared bigger or x? X squared is definitely bigger. So what that means is you write x, wherever the bigger one is, you write it. And then simply subtract your exponents. 2 minus 1 would be 1. Where's the bigger y? It's on top. So I'll write y. 8 minus 5 is 3. So I would have xy cubed. So what we notice is when dividing like bases, we subtract our exponents. So let's try a few more together. That means that we have a like bases, so subtract the exponents, m minus n. So looking at this, let's start off with our number, correct? So we're going to start off with 2 over 6. Well, 2 goes into 2 one time. 2 goes into 6 3 times, okay? And I'm just going to let this represent my fraction bar. Where's my bigger x? It's on top, so I'll write x, and then I do 5 minus 1, which is 4. Where's my bigger y? It's on top, so I'll write it on top. 4 minus 2 is 2. So I end up with x to the 4th, y squared, all over 3. Next one, once again, I'm going to start off with my numbers first. 6 divided by 2 is 3. I'm going to let this once again serve as my fraction bar. Where's the bigger a? My bigger a is on top. So then I just subtract the exponents. I got 2 minus 1, so it's 1. I don't need to put the 1. Where's my bigger b? It's on top. 5 minus 2 is 3. And then you'll notice the c's are the same. Well, if they're the same, that's like saying 1 minus 1 and or can't you just cancel them out? So when I simplify this one, I get to 3ab cubed. Next one. I got 21 divided by 7. Well, that's 3. Where's the bigger f? Here you go. This time, it's on the bottom. So now I'm going to take 7 minus 2, which is 5. Then, where's my bigger g? Well, 7/4 is bigger than 3/4, and it's on top. So then I have 7/4 minus 3/4, which is 4/4, which is 1, which gives me 3g over f to the 5th power. Okay? So now let's work our way through these.